Title of today's topic, Foundations of Localized Symmetry Mathematics. Originally, my intent had been to give a kind of a resummary of the idea of sparse information physics and bottom-up spacetime, which are themes that I've covered fairly extensively in previous presentations. Those two concepts, when you take them seriously, they give you opportunities to expand mathematics in ways that are quite different from the current focus on smoothness and differentiability. Smoothness and differentiability are assumptions. The actual physical universe, though, definitely has some constraints where you have to be a little careful about whether you're overgeneralizing your mathematics. So that was the original intent. What I actually wound up doing, though, is giving more of a specific example from a very interesting paper written all the way back in 1949 by Wheeler and Feynman. And that particular paper has some features to it that work very well with the concept of bottom-up space-time with finite amounts of information. And again, that's a theme you'll see on every talk I give, is the idea that space-time has infinite information is for me as a very non-productive assumption, because yes, you can define the mathematics. There's nothing wrong with defining the mathematics that way. But the question you always must ask is, am I generalizing the mathematics in a way that reflects reality, or am I generalizing it in a fashion that I simply find appealing? And infinite smoothness, differentiability, the idea that there's an infinite number of numbers in a small space, these are very appealing concepts. They're interesting, they're fascinating, but when we look at the physical universe, we always see limits, especially on information. Quantum mechanics is, by definition, the idea that after you get to a certain point, everything looks very smooth up to a certain point, but after a certain point, it stops being smooth. And we probably should be listening to that a little more carefully in the deep details of how we do the mathematical approaches. So we've got excellent math, they're extremely powerful, but we also want to look for opportunities to go in new directions. I've got, you see a quick overview of some of the things I'll be addressing here. It's mostly electrodynamics. And I'm going to try to keep this, I'm doing kind of an odd combination. I'm looking at a paper that really gets down into the details about some of the space-time issues, and to bring out some of what was made in that paper. Sometimes physicists say just absolutely remarkable things in terms of the implication for how reality works. And it just becomes a standard term in the papers. And some of the Wheeler and Feynman papers definitely fall in that category. They make remarkable assertions about how reality works. And yet, in many ways, they don't make a big deal about it. They say, well, this is what the math tells us. How do we work with it? But then you go back and you think about some of the implications of that. You say, what in the world does the universe really work like that? And yet, from that same work, you get Feynman's QED work, from which he got a Nobel Prize. So interesting issues. So I want to get into some of the details, particularly a paper that was difficult to read. I kept laughing when I was going over the figure, because I was going like, what in the, this figure was so confusing the way it was done. And yet the point that Wheeler was trying, and it was Wheeler, definitely a Wheeler figure. You could tell the difference. Feynman does simple diagrams. They're easy to understand. Wheeler does different. He has a different style entirely in how he goes about doing these things, but a very deep thinker. So I wanted to essentially in this presentation emphasize that work and thinking that Wheeler and Feynman did prior to QED, give a specific example, and also show how this idea of a bottom-up approach to the mathematics of that has some promise. So I wanted to get a specific example. And in doing so, I'm going to give a quick intro to electrodynamics. I'm just going to give an idea in terms that intentionally avoid the details that you need in order to do actual calculations. If you want to do the calculations, you've got to learn the math. But if you want to understand the concepts and how those concepts affect our interpretation of reality and some of the relationships, that often is a different matter, and goes back to this idea that there's little simple things that then bubble up and create the complexity that we see. theme that I've just been talking about is this idea that you have mathematics that come from inspiration in the physics world itself, not from how we want the math to work, but from what we actually see in reality. And our math certainly reflects that in physics. I mean, you see the second item, pair creation mathematics. That's the annihilation, creation annihilation operators. One of the most common events that you do in field theory is this idea of creating, like you can create an electron and a positron pairs, the classic example. There are many other examples where you're creating pairs of particles that have opposite properties with that. So one of the themes that I'm following, we'll be giving a little bit of an example of here, is that idea that we need to get underneath the continuum, and you can especially see the continuum in gravitational mathematics, where everything is a smooth manifold, infinitely precise. Get a little bit below that and use the inspiration of what we actually see in physics and what the simplest operations that we see there are. And the one I really want to emphasize is this simple idea of pair creation. And I've had previous slides where I talked about just, if you want to understand the idea of a pair creation, think of digging a hole. You create a pile on one side, you create a hole on the other side. So you have holes in these heaps. And that is the essence of the kind of activity we see in physics all the time. You get a positive charge, you get a negative charge. One is piled up, the other one's shrunk down. They always cancel out. And that's the critical constraint on creation, pair creation first mathematics, is that instead of saying that conservation is a derived property of infinite smoothness, you really flip it around the other way and completely. And you say that no, the absolute conservation is what's driving the emergence of these symmetries. It's forcing those symmetries to come into existence, because the symmetries, the complicated math, always has to go back to that concept of absolute conservation. You can create piles and you create holes, but you can't do one by itself. You have to do pairs. You have to do one goes up, the other goes down. And there's so many quantum numbers where you can do that. And you wind up getting a very interesting kind of an infrastructure that then algorithmically can produce all sorts of smoothness at large scales, but also more complicated things when you get down to the particle level. And you want that. You want to have simple concepts of smoothness to start breaking down, because somewhere this all has to be emerging from some simpler set of rules. The universe persistently tells us that it has simple rules underneath. You can't get away from that message. So we should look for those simplicities and see if we can find them, including in some of the mathematics. The time paradox of ordinary light. I'm willing to guess that most folks have not heard the message. If you've taken a course in electrodynamics, you probably have not heard the message that there's a time paradox in light, in just ordinary light. And I find that delightful, because it's there, and it goes all the way back to Maxwell's equations from the 1800s. And physicists have spent decades, actually over a century, exploring some of these little paradoxes that are in those Maxwell equations. Maxwell's equations are really insightful. Einstein loved Maxwell. Einstein was very fond of Maxwell's work, because Maxwell had pulled together and collected some ideas that no one else had really had that level of insight. He built on the work of others, but it was Maxwell who really kind of came together on this stuff. So back in 1940s, late 1940s, a fellow named Richard Feynman, an unknown student at that time, worked for his thesis advisor was John Wheeler. And I occasionally refer to them as together as the greatest physicists of the last half of the 1900s. Why do I say together? Because individually, neither one of them was as creative or powerful as they were as a team. These two made a fantastic team. And the reason they did was John Wheeler could just go wild. he would go anywhere. He'd just go anywhere. That was the way he worked. His mind was always looking for, how can I generalize this? How can I break the concept of time? How can I break the concept of space? And he loved that stuff. He just loved getting into that. Richard Feynman, in contrast, He wanted to understand everything. That was his goal. He always says, I want to understand how that works. And he couldn't do that with that broad of a view, but he could take those ideas and then he could pull them in and say, well, how about if we control it a little better? How about if we force it into equation? How about if we do some kind of approach where it winds up producing a testable result? So you put these two in a room together and they spend a lot of time with each other. They respected each other highly. They really got along well. And then they would come up with these ideas. And especially because of Wheeler's influence, they did not mind exploring wild things. It's interesting, after they separated, there's a noticeable drop off in the creativity of Feynman's work because Wheeler was the one who was poking him. And by the way, when I say a drop off in creativity, oh, that's relative. I mean, Richard Feynman still just casually did things like invent quantum vortices and superfluids almost without even thinking about it. So dropping off in creativity is a very relative scale, but he certainly um, didn't have the same kind of creative directions, looking at different directions. So you see, as quantum chromodynamics is in many ways just an extension of quantum electrodynamics. And Wheeler kind of kept him away from that. Wheeler got him into interesting sets of thinking. And one of the most interesting sets, I'd say, was this whole idea of the photon paradox and how this worked. And the problem goes back to the equations and the idea of, oddly enough, of just where do you get this little kick that you get from a photon? What an innocent sounding thing. When you turn on a bright light, you see this concept in photon rockets. If you've looked at some, it's not just science fiction, it is an actual concept that's been presented. If you put a very bright laser out the back of a spacecraft, it becomes a propulsion system, and it has some very nice properties. It has some difficult properties, and you certainly don't want to be in the receiving end of that laser. It's one of the problems with the photon rocket. But nonetheless, it's a very efficient for certain types of applications method of propulsion because you get a little kick from those photons. They push against your spacecraft. Now, here's the weird thing. That seems so straightforward. You run into it and you just say, yeah, I got a photon shooting out. It's a rocket. Maxwell's equations don't say that. They don't give you that, at least not in the first iteration of it. And this baffled physicists for a long time. They're going like, wait a minute. If I give off a photon or if I accelerate a photon, there's this effect was a recoil effect that gives me this kind of bump. But where's it coming from? Because it's not actually in the equation. It's an idea that you accelerate your car and you keep on coasting, you don't suddenly get a kickback that slows you down. So that's the general idea. It's like you're accelerating your car, and if your car is a photon, then you suddenly get this little bump back. So wait a minute, no, you just gave me some energy. I'm going to slow you down. I'm going to go off and give that momentum to somebody else. And this was baffling because the photon, as according Maxwell's equation, wasn't doing quite what they thought it should do. So people looked at this for decades. There's a whole list of names of people who examined this problem, and Wheeler and Feynman decided to get into it. And Feynman, he even tells stories on himself about how he completely misinterpreted the problem at first. He didn't understand what Wheeler was saying. He made some actually silly ideas, and it's an interesting thing about Feynman. He doesn't mind telling stories on his own stupidity. And he's not a very stupid guy, so he didn't have many episodes. But when he did, he would tell them on himself. That was one of the examples. So Feynman had trouble even understanding what Wheeler was talking about in some cases, and it took him time to get into this. So if you look at these titles, you got two papers: Interaction with the Absorber as the Mechanism of Radiation. Now, isn't that an innocent sounding title? I mean, it just sounds like a techie title. It's not. What that's actually saying is that something weird is going on in time because the absorber may be a billion years in the future. So even the title is saying something very unusual that comes out of this question because it says, well, the absorber of the photon, which may be way off in the future, shine a laser out in space, those photons are going to travel for a long time. And yet, even in the title, Wheeler and Feynman are invoking that as saying that's part of the radiation mechanism itself. It's part of the recoil, in fact, some of the kickback. So another paper kind of summarized it in 1949, and that's the one where I'll be addressing mostly in this, explaining Wheeler's diagram, explaining his figure a little bit about why it's such an unusual figure and why it is such an unusual message. This didn't end with these papers. After this, Feynman went on to do quantum electrodynamics. Quantum electrodynamics was very much inspired by this work, but also takes it to a whole new level. So there's a connection. These aren't just events that happened and nothing came from it. Some extremely good work came from this. I want to show the figure first because I'm going to be getting into just actually much easier stuff, just talking about electrodynamics and kind of a quick intro to Maxwell's equations, because that's where it comes from. So you need to have some basic understanding of Maxwell's equations to see why there's a problem here. But here's the two figures that he had, which like the first figure, the one on the left, he doesn't actually introduce it until he's actually started talking about the second figure. And then he starts talking with terminology that he hasn't introduced anywhere. So it's just, and in terms of how to write a clear example of a figure. This is not a stellar case there. So you can tell that Wheeler's mind was zooming around in this. He's saying, "Oh, this is really interesting," and he has the idea, but he has some difficulty trying to present that idea and carry that idea over. And again, I keep blaming Wheeler just because Feynman's diagrams are so different. This has had to be heavily a Wheeler type of diagram. So in his diagram, well, the first thing I did is he talked about times in a day, AM and PM and gaps of 5 hours. So just for simplicity, let's bring that down a little bit. So nanoseconds, 1 nanosecond is the distance light travels. Light travels 1 foot in 1 nanosecond, to a very close approximation. So let's just make this a little more lab size, and that's what these figures are doing. And then he has this interesting uh, puzzle that he comes up with and says that, it seems to be that there is a future connection in the absorber that then somehow comes back and impacts that. Could we make a device that would actually detect that? And if we can do that, can we create a paradox that you then have to say that, oh, time's going to have to diverge in two different directions for this to happen? You literally are seeing what you're into the future to what you're doing. And this is what Wheeler came up with. And it is a fascinating and deep paradox. But unfortunately, I think it's not gotten as much attention, partly because it's like I say, it's kind of confusing when you go through the paper and you're saying, like, what is he really saying with this? And so bringing it out is worthwhile, because the thinking is very deep. It's just that the presentation is a little hard to get to. So I'll be getting back to this. I just want to give a quick advance to show that even though I'm going to be going through some very simple stuff, the goal is to get at this very intriguing representation that Wheeler came up with. The second part of this that shows what I'm talking about is, I'll give you a quick intro to the actual paradox itself. When you send out a photon, it goes in two directions. You have, into quantum level, quantum space is four-dimensional. It's not three-dimensional. And you have time. You hear this statement that the laws of physics work the same in both directions in time. That's true. But when you work at electromagnetic radiation, it becomes especially unusual because it means that your waves can go in either direction. It's just a simple sign change. The waves work the same way. So in a nutshell, what Wheeler was saying was, if I have a jiggle of charge, and then that creates an electromagnetic wave that goes into the future, no problem. And then it also goes into the past. And this is the problem that so many physicists have struggled with since the 1800s. and say like, wait a minute, that doesn't make any sense. So people, the reflex reaction is say, well, we'll just discard the past solutions. Those can't be valid. But as soon as you do that, you lose the recoil. You lose this effect of the fact that you have a slowdown of that you somehow you're transferring momentum to that future particle. And this is a conundrum that Wheeler and Feynman put together into an actual example where you get a wave going in the past, it bounces off of another charge, easy to do, it's not a complicated process, and that in turn creates another backwards wave that goes this way. So you're getting this interesting combination of radiation events. So this one's also producing a forward wave, but it's also producing a backward. And the bottom line is, here you are, you shake a charge, and then you look at your records, your lab records, and you say, oh yeah, I see that I did that 10 nanoseconds ago. Oh, I should have noticed it then. So, well, I didn't notice that I jiggled it 10 nanoseconds ago. And then Wheeler and Feynman with their little device come up with a way to say, well, can I make that into a time paradox? And if so, what's the resolution? So that's where I'm heading. And now I want to just get into a little bit into this is like a quick course in Maxwell's equations, intentionally avoiding all the detail that you must know if you actually want to actually use these things. But the geometric, when you go down the level of the algebraic constructs, the relationships, a lot of this is surprisingly simple. You have all these constants, but you don't really need to get into the details of the differential part. And also, again, some of these equations, because they're differential equations, kind of ignore the fact that it all starts with just simple pairs with very discrete charges. No one ever sees free charges of less than 1 electron unit. And that's a constraint on the mathematics. We can say that, well, I generalize and think it could be anything, but that's not what we actually see. And the quarks are a very interesting case. That was something for some other time. So you want to, if you want to use Maxwell's equations, you need to learn the full set, and there's many excellent representations of it for different applications. But you want to look at these issues that are producing these time problems. Pair creation. This is not where you normally start electrodynamics, but this is where, because I'm taking the viewpoint of bottom up and that we should take a stronger clue from physics than we do, then in the full Maxwell equations, you just have the concept of charge. It's not quantized. It's just an entity that you have that could be infinitely small. So, which is reasonable in Maxwell's time, because they didn't know about the electrons. They didn't know about quantization of these issues. They could only see lumps of charge that seemed to be quite smooth and quite continuous. But that's also the danger, because if you see everything, it looks continuous and it looks smooth and it looks like that, it is so tempting to make the mathematics equally smooth and differentiable to an infinite limit. So the reason I start off talking about Maxwell's equations with pair creation is because that is not what we see in physical reality. The universe that we're trying to model with our mathematics does not begin with infinite differentiability of charge. It begins with lumps of charge, and it's an extremely specific process. It's a hole and heap process. You have a hole on one side and you have a heap on the other. We label the minus sign, the electron, as the hole. We label the proton very arbitrarily as the heap. Although if you go on deeper levels, they may, at some point, I think we may get to a point where there actually is a relationship between these charges in the direction of time. So it may not be entirely arbitrary in that, but it's certainly the starting point where we see actual charge begins at this energy event. That energy event, incidentally, in a very real sense, you can take two photons, take an extremely high energy gamma photon, collide it head on into a green laser. I think it's the first version of I saw that actually did this. And it produces a positron and electron. So you go like, wow, okay, I can use pure energy in the form of a photon to create a pair of charges. And this is just a beautiful little microsymmetry that causes all sorts of interesting things to come from that. If it was only positrons and electrons, we'd be in trouble because the whole universe would go. collapse back is that problem about where does all the baryonic matter come from? Okay, so you got two things called positive and negative charge. What in the heck are those? Well, there's many ways you can represent this, but one of the ways that I think for understanding intuitively what these things do is just a good old field lines representation. We've all seen this with magnets, and which are very closely related phenomena. And you can do it with electric charges also. So you get these lines where it looks like there's a connection, a little pathway. And in a case of like iron filings, it's a literal pathway that connects this magnetic force, kind of concentrates it a little bit, and it has a direction to it. So in the case of electrons, we arbitrarily say that it's coming from the positive and going out to the negative, and it likes to fill space. And that's important. It doesn't just go in a straight line, just go from, from the positive, it doesn't just go straight from the positive or to the negative, but it says like these guys don't like each other. Maxwell called them quantum vortices. He had this whole delightful model in which they were like little tornadoes, and they would whiz around, they would expand, and they would push against each other and try to go out in different distances. And he later replaced that with differential equations. But before you diss his quantum vortex model, his molecular vortex model too much, that's how he figured out that light was electromagnetic radiation. So it was a powerful model. And he used concepts like this, the idea that these, for instance, these lines would literally be little vortices that are going out and rotating, pushing against each other, doing these things. A little side note, if you get into standard model of particle physics, when you talk about the color charges, they don't do this. They attach more or less in a straight line, much more like a rubber band. So they don't resist each other. They don't pull, they don't push out against each other like electric charge does. They just kind of lock on, and the farther you stretch them, the more upset they get. So there's more than one way this can happen. And so it's important to notice that there are different configurations, different micro configurations of this concept of field lines. Can you represent electromagnetics in other ways? Of course you can. There's all sorts of equivalent representations. But field lines, as Maxwell noted, provide a particularly interesting way of understanding the relationship between these charges. Now, what Feynman did, I mean, not Feynman, I'm sorry, Maxwell did, is he was, I don't think he introduced the term, but he liked to use the term flux. Now, if you recall your linguistics, your etymologies, flux just means flow. It's a flow of something. Uh, Maxwell literally viewed these lines as a flow of something like a fluid going across these two locations. Now, when you're talking about batteries, it's a literal flow. You have actual electrons flowing from one side to the other, reverse polarity, unfortunately. But he was talking about something a little more subtle. He was saying that we see that same effect even between these static charges, that it looks like there are these pathways where you could think of it as something was flowing there, even though it's static. Nothing's moving. It's not giving off energy. It's not radiating. Nonetheless, it seems as though there's a path. And the odd thing about that path is you have a source, you have the positive side, you have a drain, and then it just sort of disappears. And it's one of the obvious questions is you look at Maxwell's model. I remember the first time going through some of these models, I'm like, and where does the flux go after that? And that sounds like in some ways like a silly question, but I don't think it is. I think there's something that nature is trying to tell us about the relationship of charges that we still haven't quite figured out, because there is some kind of a connection, there is some kind of a loop, but we only see half of that loop when we're talking about a positive and electric and negative charges. That's interesting, because if that wasn't true, we would not have a physical universe as we know it. The fact that we can only see half of this flow cycle is incredibly important for the existence of things like electrons, for the existence of things like protons. So there's some little bit of trickery going on in the deeper physics that we don't really understand, nor do people really worry about it very much. But I would suggest that that's actually a very interesting thing to worry about. And one reason why you could argue that is that in the case of magnetic lines of force, you don't have this problem. That is the single biggest distinction between electric and magnetic. When you have magnetic lines of force, they're also flux lines. They also seem to come from one direction, go into the other, but they're always, always, always eventually looped. They never go to a point. They never go to what would be called a magnetic monopole, at least not that we've ever seen. Valentine's Day event accepted. Good luck on that one. That's always an amazing story about finding a monopole on Valentine's Day in a lab that was not attended. No one was ever able to reproduce it, but it was a fascinating result. So observationally, we see these two kinds of flows like this, these two flux concepts in electrodynamics, but only one of them is able to terminate at a source and a sink, and that's the electric force. The magnetic force is remarkably similar. There's some scaling differences, but just like the electric, the magnetic field lines don't like each other. They try to get away from each other. And you have all sorts of interesting effects with magnets because of that. They pull in one direction, they expand in the other, which again goes back to Maxwell's beautiful little vortex models where you have these little tornado-like behaviors where they're sucking in one direction and trying to expand in the other. So it's a delightfully physical model that Maxwell used to great effect to understand what's going on with that. So the net result is you get these loops, but you don't get the charges. Now, electric can do this also. However, electric can do both. So you can have these loops with electric, or you can have these loops with magnetic, but you can't have the termination points with the magnetic. So an interesting broken symmetry. Interesting. I mean, I remember one of the earliest ideas I ever got into in physics was I was um, a very long time ago. Um, uh, I got fascinated by this and wondered if there was some kind of magnetic equivalent of the electric and positron particles. And small town library, I didn't have very good resources. I finally ran across some guy named Dirac had come up with this idea, and I thought, oh shoot, it's been known for a long time, but it's a fascinating little symmetry. Now, the most complicated equations in electrodynamics deal with the issue that you see in these two cubes. Now, the more you get into it, you really have to get into your differential equations, you have to get into the relationships, but the idea is not complicated. In fact, the name of this even reflects what's going on here. It's called a cross product. And if you look over in the left-hand figure, you've got an electric line of flux, just like I showed before. But let's say you move that thing. So relative to you push against it, you move it this way, move it out towards the back of the cube. What does that do? What that does is create a magnetic line of flux, and it's perpendicular to the other two. This is why it's a cross. It literally forms a little right angle cross here. And then the product of that right angle cross is a third dimension, is this dimension magnetic flux. Maxwell got this from something called quaternions, which are the four-dimensional equivalent of complex numbers. There's a little thing that in the math of quaternions that has this cross product capability. And boy, did it prove useful for a lot of physics, because when you're working in three-dimensional space, there are all sorts of things where this idea of you have some kind of a force line here with a direction, you have some kind of a motion, and when they're exactly at right angles, you get the maximum product going in the other direction. And then you have another thing called a dot product that tells you what happens if it's not at a right angle, which is just basically a shadowing effect. You take the part that is at right angles, and that gives you the cross product. The dot product tells you, says, well, if they're not at right angles, what happens? And the answer is that if they're completely parallel, nothing happens. You have these sets of relationships. All of this comes out of quaternion math, but it was just broken apart into these two concepts. And the symmetry is that magnetic flux and motion does the same thing, except it produces electric flux. So not too surprisingly, put these together and you have the basis of a lot of electromagnetic radiation. You have radio waves, which have both of these components, they trade off between each other and produce different ways of looking at the same packet of energy. Now, if you go back to what I just covered, I just say pair creation, force lines, magnetic force lines, that you cannot have terminus points for magnetic. You can have them for electric. And then you have this interesting thing where you have these cross products. Everything I just said is in these four equations, which again, Maxwell pulled them together, and but they were already, for the most part, known in other areas. So he pulls them together. But if you take a look at this first one, there's two different ways to represent it. You have the form on the left is a differential form. The one on the right is an integral. In many ways, this is almost like in the top right line. It's almost like a pictographic representation of what you're doing. This little oval that they show with the integral lines. This is where you're just circling around. You're saying, I want to have a complete surface and want to make sure that everything is covered. And the message from this is it really is just that charges exist. Something called charges exist, that within an area, you can have a certain amount of charges, which actually turned out to be electrons or protons. And then once you have that, you're going to have a fixed number proportionally of these field lines coming out of that. So you can measure the amount of charge by giving a standardized, you know, definition of these field lines, which again, they always trying to spread, so they become more diffuse. But nonetheless, you've got a total amount of electric charge-ishness coming out of that volume. And that's really all these first two are saying. They're saying it in a form that looks a little intimidating, but they're saying that if I have a closed space, I either have electrons in it or I don't. And if I do, then I have this integral. I have this non-zero sum that rho over epsilon sub zero. I have this non-zero sum that tells me essentially how many electrons or how many protons do I have in that space. So complicated ways of doing it, they give a lot of precision, but the concept is very simple. By the way, it does not say that electrons are points. In fact, it actually avoids that. It says that in a volume, you will have a certain amount of charge. And that's an important distinction, because if you go into the quantum side of things, the smaller you make that volume, the weirder it gets and the higher the energy gets, until it gets to a point where it just starts breaking things. So the idea of reducing these charges to a point is something. This frustrated Feynman his entire life. He was never satisfied with his own understanding of what happens when you shrink that envelope all the way down to a point-like size. The second law is just saying you don't have monopoles. That's all. I once had an opportunity in high school to explain to a physicist who was there for promoting her college, and she was kind enough to let me to explain to me these first two laws. Because I was proposing to her, I said, well, isn't it possible you could have magnetically charged particles, was what I was asking. Again, small town, I didn't have anybody to talk to. And at the very end of the conversation, she had gone through the second law here. And I made the mistake of saying, well, this is very interesting. Thank you very much. But didn't you just say that there are no monopoles because there are no monopoles, which was exactly what she had just said. She had quoted exactly the second law. So so much for my political skills. This did not go over well. She got quite upset at me, but it was not because I was wrong, because that's exactly what she was saying. She was quoting the second law, but she was kind enough to go through the discussion for me. And the second two groups, these are talking about the somewhat complicated relationships of those cross products, dot products, and how this all gets together. And of course, you have that charge issue, which further complicates that. But keep in mind, again, the equations look complicated, but the concepts going on here are not that complicated. They're straightforward things with a very strong geometric interpretation. And that geometric interpretation can help you understand how these things will interact in a given situation. And I am having trouble getting there it goes. For some reason, my slide wasn't moving. Okay, now, given all that, I want to give a little shortcut on understanding the concept of waves, which is this. Remember, I mentioned that Maxwell really viewed these as a flow. He viewed them as some kind of flow, of a strange flow. It was a flow that had a hidden dimension, essentially a little subspace where everything just suddenly magic went from one spot to the other spot and started to cycle all over again. And none of this gave off energy. It was all static. But still, he had that model. He liked that model. And there's reasons why I like the model, because if you interpret these lines as being like essentially a very tiny little chunks of charges, but a unitary size of some sort, not a real size. You can't do this in the physical universe, but it does seem like they have little charges, and then they start out one side, and then they go out a little bit. Time equals 2. Again, this is arbitrary. You're just saying this is how it works. Time equals 3. Keep on going out until finally you get to the other side. So what's the importance of all that? What's the big deal? Well, the deal is this. All of that motion in terms of understanding how light waves work, how radio waves work, is that you have to understand that these field lines are just as bound by the speed of light as anything else in the universe. Speed of light is a really, really hard limit. So if you go back, I may be missing a slide. So it's a hard limit, and it applies to all of these concepts. So you don't just have a symmetrical bunch of lines here. If you want to disturb something, if you want to make a change to it, you're suddenly going to hit this influence of the speed of light. And what that does is, if you look at one line, say this is one field line going from the positive all the way over to the negative, and you say, well, I'm going to start jiggling that thing. And what happens is you have to respect the speed of light. If you view that field line as a stream of little particles that are, tooling along, heading towards the drain on the other side, then as you jiggle it, you've changed the position at which each of the particles is emitted. So you plot that out, and what you wind up with is, from this, just really from a particle viewpoint of these little interpretation of these lines, you start getting this wavy thing, is what we think of as a radio wave or a light wave. And it is strictly protected by the speed of light. So a very simple way. Now, are the actual dynamics more complicated? Oh yeah, because you've got this whole thing I was saying about the cross products, electric field, magnetic field. So it's a lot more complicated than just this. But in terms of why you get a wave, this is kind of like the simplest possible case where you say that if I start jiggling things that have charge, I will get a wave. One way or the other, I'm going to get a wave. The variety of waves you can get, the kinds of waves you can get is enormous, but you will get a wave. And here's where the problem is. It's just, and I kept looking at it and saying, there's got to be some complicated way of saying that, people worked for decades and they figured out that, no, it's none of that. It's, if you put a negative sign in Maxwell's equation, you still get a wave. So if you put negative time, you get a wave. It's as simple as that. The equations are not that complicated. So this is the problem, is that if you use Maxwell's equations as they're written, and they seem to be very, very good, so nobody can think of a good reason not to, then you wind up waves going in both directions. They go forward in time, they go backward in time. The reflex response for most people, a number of people, I think Tetrode was one of them. I love that name, Tetrode. But there was a number of people, they said, well, we just, yeah, fields don't work that way. You just arbitrarily say fields don't work that way. They can't go backwards in time. And that was kind of the default position for many people for many decades. But again, it's not what the equations actually say. And what they say has a simplicity. Whenever an equation gets very, very simple, you want to be careful about ignoring the implications, because when it's the simpler it gets, the more likely it is it's trying to tell you something and you may not be listening because it's a little bit counterintuitive. And this is a good example of that. So this is the part they probably didn't teach you in your electrodynamics course, is that, oh, by the way, this all goes backwards in time also, because you go, no, it doesn't. I'm making a radio, I'm not worried about my radio wave going backwards in time. There's a very pragmatic way of interpreting it and say, well, that can't be right because time doesn't work that way. Electromagnetics don't work that way. But if you start looking at a level of particle physics, wow, you have to start being a lot more careful, because we can say that at the universal level, we don't see this, or we think we don't see it. And that's a good point. We think we don't see this, but in fact, if you go on the deeper level, you do start seeing stuff like this. And when you're talking about electromagnetic waves, they're wall huggers, not face huggers, wall huggers. They hug the wall of the light cone. So the blue there is the forward light cone. This is where you're going forward in time. And if you're electromagnetic and you're in a vacuum, you're going to go either this way or that way. In fact, you just go in a sphere that radiates outwards. It's just obviously a very small subset of that. So if you do this wiggling here up and down, you're going to get waves going out this way in time and that way in time. And you're going to have also, oh, by the way, it doesn't, when I say in a vacuum, if you're not in a vacuum, this line can get very much more vertical. So optically dense material will slow it down. You'll be more inside the light cone. Some of the fascinating work in actually stopping light would put it in this central part here. So I mean, that's to me, it's the most interesting work of the past 20 years is where folks have actually stopped the speed of light completely and essentially frozen it in a medium and then let it start moving again. So in a vacuum though, these waves will radiate out from your location at the speed of light. And also, according to Maxwell's equations, they go backwards. And what do you do with that? Now, this is getting closer. This actually is representation of what Wheeler was pointing out. Wheeler is pointing out and saying, well, you know, if I go backwards in time with one of these waves and I hit another charge, then that charge is going to start wiggling, not as strongly, granted, but it's going to start wiggling. And then when it does that, it also is going to emit waves. And guess what? Its waves also go forward in time, which I have not shown because that's not the point of this one, but also backwards in time in the opposite direction. So what happens is you find this thing that I mentioned earlier on, that if you take what's called the advanced solutions to Maxwell's equation, which just means backwards in time, take the advanced solution, you wind up saying that one way or the other, and it may not be a big effect, but I am going to bounce off of mirrors and I'm going to wind up here. And by the way, this charge could be a literal mirror, not just a figurative mirror. A literal mirror is, in fact, a bunch of X-ray level energy electrons in Fermi space, and they jiggle. And when they jiggle, they send it back. So this is not just necessarily a figurative mirror. This could be a literal mirror. So it's saying that if you have a mirror and I do an experiment here, and that mirror was still sitting there, 5 nanoseconds earlier, then this advanced wave is going to reflect off that mirror and head back to me, back at 10 nanoseconds, minus 10 nanoseconds. Uh, how much do I have to say to emphasize that that could be a problem with causality? So, we see all these you see all these time traveling science fiction stories, and maybe this is a missed opportunity, but nobody ever talks about the time contradiction in light, in ordinary everyday light, in electromagnetic radiation, and the fact that when you do a radio wave, in some sense, it should go backwards in time. Um, Frequency, I think, was a movie maybe that did kind of explore that because they use aurora borealis effects to kind of go backwards in time and let people talk to the task. So that's the nearest I can come to a movie that may have actually explored this issue. But is it a real physics issue? Oh yeah, yeah, and so much so that um, it has given field theory people fits for years, for decades, because if they get rid of the advanced wave, you lose that recoil effect I mentioned earlier. You cannot reproduce what we actually see if you get rid of the ability to send momentum back to the earlier point in time. Well, so Wheeler looked at this and said, well, what can we do with this? And now we get back to the figure I started out with. Wheeler came up with this clever. I would still like at some point to go over this even more carefully and see if I could come up with a version of this figure that better captures the later work by Feynman about Lagrangians. Because I know there's a way to do this, but at this point he was just emphasizing the paradox. And the idea was that this is that same wave that I just showed going backwards in time, and it hits here. So you got 5 feet, so 5 nanoseconds. So you get this bouncing. So A sends off a wave, it goes over here to B, then the B sends it back to A, which does not show up well in this diagram at all. And it jiggles this lever. It jiggles this lever, so it pivots down a little bit, and it blocks the falling of this pellet. So you have this kind of clumsy, but still also clever point that Wheeler is making that says you can make a physical, actual device in which the advanced wave, the wave that goes backwards in time, will have an actual physical effect on the system. And then he goes into analysis, and again, this is one where I think there's a better solution here, but his way of dealing this was essentially saying that there's a combination of attenuation and of your effect is attenuated, and it's a continuous issue. It's never just a fully discrete issue. It's something where you have this slow motion, and the motion has some finite level at the speed at which it progresses. And his point was that what happens instead is you get a negotiation. So you get a point where it, like for instance, the pellet nudges against the rounded corner, but it's not completely stopped. And the two kind of work together until they finally say, like, yeah, okay, you want it this way, I want it that way. We're going to compromise. Pellet's still going to hit the pivot. We're still going to get the thing. But you did get to bump me a little bit. You did get to change what I did. And think about that. What Wheeler was saying here is that, yeah, you can't split time into two parts. You can't do the time paradox with this. But you can affect the past, and you will affect the past, and you have to affect the past. So it's saying that not only are the advanced waves real, Wheeler's argument was that it actually is part of the physics that we see with that recoil, that when we have that recoil, we're actually going back in time and taking something from the future and applying it at this early point. So just absolutely fascinating argument. Again, I wish this figure had been better publicized, but I think QED kind of took over later, and people kind of forgot this idea that these aren't just mathematical abstractions. These are actual physical effects that we can measure using devices, but they converge to a single solution. So one way I've tried to think of it personally is it's like there's another dimension of time that we don't see, that is the resolution time. So you get this, and you could see this in gaming. People can understand this concept quite easily. There's the point in which the pellet's falling, the pellet's hitting, everything negotiates. The advanced wave, the advanced wave and backwards in time, they negotiate with each other until they come out and say, there's a single solution that will work for both of us. And then that becomes the actual physical reality. Now, I'll put a comment immediately. Notice how different that is from the multi-world situation. The multi-world solution, which Feynman did not accept. Feynman, in fact, was the one who criticizes, well, you're going to split the universe into a gazillion pieces if you do that. So Feynman did not go along with that. Feynman's idea, the idea in this, and Feynman's later work, is that one way or the other, you work all these different possibilities together, and you wind up with a single outcome, a singular definition of what's going on. So it's a very different perspective from the many worlds perspective. However, I would also argue that, which is weirder? Okay, you can have multiple universes, fine. So universes all over the place. There's a little mass and gravity problem with that, by the way. But is it any less weird, the idea that an event literally billions of years in the future could affect your measuring device in a lab now? I think that's pretty weird. So it doesn't mean that you're changing history. And again, this is a negotiation. It's saying like, some particle a billion years in the future is saying like, oh, all right, let's come to a conclusion here. Let's do it this way. This is just fascinating work in a way that's very different from many worlds, which I'm not a many worlds fan. In fact, I just think I have seen people propose that Everett Minute is a little bit of a joke, and I actually think he may have, because he never supported his own theory after he came out with it. He actually hid from it. So something weird was going on with that. But this is a different and a much more experimentally verified version of what's going on. So it has implications for other parts of physics. So their conclusions: advanced waves are real. That you really do have this. This is where they went with this. So it affects what's going on. But the combination of the continuity of the action, in fact, there's no such thing as a truly discrete event, and the fact that things always attenuate, they always go. And Feynman got very specific on how this attenuation works later on with his QED theory. It's just this whole variational model is just beautiful, the integral of all histories. So Feynman went on to get a much more mathematically precise version of how this negotiation works. But it's still just fascinating, the idea that there's this connection between what could happen, what will happen, and what's going on right now. And that our definition of now is a lot more, if you take that, just take that at face value, our definition of now is a lot more nebulous than we think it is, because what I do right now, especially if I'm measuring a quantum event, it actually has pieces and fragments from some history that has not happened yet in my time frame. And so this is not predestination either. This is something a lot more complicated than predestination, because it's interactive. And it's not saying that the future determines what's going on now. It's saying that when I try to make a determination, I have to take the future into account. Now, recoil is the issue. That's the one I want to point out very simple. It's such a simple idea that, again, you take out a laser, you turn on your laser. If you have good equipment, you can measure a recoil after that. And incidentally, the models for that are a little bit fuzzy. And I think not accidentally. The models for that are a little fuzzy on exactly, well, how does that recoil part work again? And I think part of the reason is because there is this connection with the future. It makes it a little tricky to try to map that. But you turn on the laser, you get a little bit of recoil, and that recoil is coming from some very distant point of the universe in both space and time. And yet that's the only way you can explain it with Maxwell's equations. So strange, especially, I always like the experiment. If I shine laser, I find the darkest spot, the darkest hole in the universe, and I shine a powerful laser out there, I would still get the exact same recoil effect that I do now. And yet that recoil is coming from something that is so far in the future that we don't even have the mathematical models to understand what it looks like. We have no idea what matter, what organization matter. Will everything be black holes by then? If it's black holes, how does this work? There's a lot of interesting philosophical questions and actually physics questions about how that works. If you can you find a spot in space that is so dark that you actually don't get a recoil effect? Remember, I said there's a little bit of fuzziness in this recoil. Just some very interesting issues involved with such a simple concept. And Feynman and Wheeler certainly explored that. Now, the thing I want to point out, and this is now I'm getting back, I said this was kind of for me an example of sparse information physics and a bottom-up space-time physics, which again, those are two concepts I've got plenty of past presentations, so there's no point in rehashing some of that. But the idea that the universe has a finite amount of information, it simply doesn't have enough resolution to go beyond that detail. You're limited by mass and energy, just like you're limited in how much storage you have in your computer. So a lot of quantum mechanics comes not from fuzzing things, but from the fact that it's not there. You have to construct it. You have to construct the details. So Maxwell's waves were never quantized. Maxwell was pre-quantum theory, but he had these waves going back and forward. And what quantum theory gives us is a new insight that we didn't have before, that there is a way in which these waves can become extremely tightly paired. and we call that pairing a photon. The pairing is that you have a forward wave that's going as we would normally think of it, um, and you have the backward wave, the advanced wave, that's coming back, and the two sometimes, and actually it's very rare, sometimes the two can kind of do a collapse. They just kind of go, and they just lock together. And when they lock together, you have a photon. The locking operation ties that photon, that two-way interaction between two very specific particles out of a universe of possibilities. So think about that. How many possibilities are there for a photon going out into deep space? And the quantum probability you can calculate is just absolutely enormous. These things, the photon could go anywhere in the universe. And yet, at some point, it undergoes a collapse effect, and suddenly the two possibilities shrink together, wrap around each other, and becomes a specific transfer of momentum, a specific transfer of energy that is quantized. You don't lose the energy. You don't lose the whole wave becomes something where you have this double effect. Now, what I would argue is that, and again, this is a hypothesis, but one I would strongly propose is that if we want to understand how quantum uncertainty works, we need to focus more on just this problem, this idea of how do these wave structures, these combinations of Maxwell waves going forward, Maxwell waves going backwards. There's other variants of this with other forces, but those are the ones that are most experimentally tractable. Is at some point it seems to create a house of cards, and some kind of event, and we don't know what. This is when everybody says, like, we don't know exactly why does the photon go there, but this at least gives a framework for talking about how that happens. That you have these two-way frameworks, and then at some point, especially when you push a paradox, and I think somehow that's a key idea there. When Wheeler pushes the paradox and he says, I'm going to make it so that we'll force it to either go one way or the other, that sort of instability, if you think about it, it's almost a necessity, has to trigger a collapse event in which suddenly it becomes specific. It no longer has the option for going one way or the other. So the idea of creating a paradox seems to be part of this issue about how did the two waves, the forward and the backward wave from the Maxwell wave equations, how do they suddenly turn into an actual quantum event with a very specific momentum and energy transfer? And the creation of a paradox seems to be part of that. If you force it into a direction in which it has to make one decision or the other, at that point, it also causes this immense collapse. Again, there's a kind of a concept here. There's a different kind of time. If you think of us being it's gamers know this. That you can have you have your own time that you're watching what's going on in the game, and this would work somewhat in that fashion, which you have this idea that in that broader time, all of this can just suddenly go, and you wind up in getting this photon. This means that photon is not a particle. And apologies to Einstein. Einstein said that the fact that photons can be quantized on emission, quantized on reception means they must be a particle with a specific path in between. I, that is just not what we see. It just isn't. I mean, we have all sorts of complicated models to try to say that, well, there's the particles there and there's a wave around it, and you get very complicated. But observationally, what we see is a kind of a collapsing event in which you have these different wave models suddenly come together. And I think that is a kind of a deeper aspect of what it is to be a photon. It's not so much that, because the path in between those two spots can be unbelievably complicated, large, time-consuming, whatever attribute you want to put to it. But the result is tied down at two ends. But the in-between, you don't really need necessarily to make it all extremely precise and particle-like. You can, but the chances are you're going to wind up complicating the model instead of simplifying it. So I would suggest that photons are actually an extremely interesting and rare statistically speaking, collapse event that happens with combined Maxwell waves, advanced and forward and advanced. So where to next? Again, this is part of what I'm doing today, is giving a little insight into some of the things I've been working on that. Same things I was just saying. There's a quantization, not a paradox, but a quantization effect. And I think the math that we need to understand how quantization happens and possibly have some better way of controlling it a little bit. I don't think quantum quantization is a completely forbidden territory. I think there is some possibility with that. The example I gave earlier, you shine a laser into the darkest part of the universe. Does that affect the photon wave functions going in both directions, the waves in both directions? Probably does. Is there a way that we could actually do that? Hard to say, but there's some kind of an effect. This is, at least gives a framework for modeling these houses of cards and then talking about how they resolve when you try to force a paradox on them. And again, forcing the paradox certainly seems to impact that. This is a more complicated view of the universe. It just is. And I think it's coming directly out of a lot of the work that I mean, the only thing I'm really adding here is just the assertion that the photon events are rare, and it's kind of like stating the obvious. They're rare and they could have gone in many different ways, but when they do, they produce what Wheeler and Feynman were talking about in this paper, is a very specific action. Suddenly it quantizes and chunk, you get this resolution that matches all the conservation properties that are required, does not create new universes. I don't know how a local event would do that anyway. There are speed of light constraints, but it captures all those things. Speed of light, by the way, gets interesting when you have speed of light going backwards. when you have the speed of light coming in from the future, that I think it's kind of amusing what you mean by speed of light. Speed of light is very strict, but it can go in both directions. So how's that for a strange concept? So what we are now and how things work is somehow related to things that have not happened yet, but it's not predetermined by things that have not happened yet. So this is an interplay. This is a calculation. And it's also why I would make a final comment that if we want a better quantum computing model, I think we need to pay more attention to these levels of interaction. And I would specifically say that the forward and advanced wave model, the Maxwell equations, quantized and understanding how that quantizes could probably be something to help us get a better quantum computing model. The Deutsch model of multi-worlds is very tempting. It's very attractive. It phrases all the computation in terms of just multiple universes doing it. I mean, I was a period, I love that model. I used to really like that model. I thought that was a great model until it didn't work as well as it was supposed to. Then I started getting more skeptical about it because they even said back then, they said, well, we'll find out soon if this works. And that didn't happen. What happened instead was everybody started making excuses. Well, the problem is the noise, it was sad because at first people were very emphatic that it would either be true, it wouldn't be true to prove the many worlds model. We've kind of dangled on with that model for a long time. So let's go to a different radical, weird model. Let's go to the idea that quantum computing depends on future events, because we have some actual experimental proof of that. And even things as simple as recoil tell us that. And we still don't have that fully tied down. There's probably a connection there. Where the more we understand that, the better we will be able to understand how this goes. One other comment I'll make is when you look, and I don't know where I call this a speculation, but it just is fascinating. One electron here is the same as one electron on the other side of the universe. There's another one that Wheeler loved. This is exactly the kind of turf that Wheeler would get into. So, he had his theory for one electron bouncing back and forth between the beginning and end of time. But if the future is setting properties now and determining things, maybe there's some aspect of this idea of interaction with the future that's also helping to set the most fundamental properties of our universe now. That is, it's not independent. There are constraints on the future that at the same time help to say, hey, all your electrons back here are all going to look the same. You got no choice, because the future is helping to set that in a fashion that we can't directly see. So I think there's some interesting possibilities just on our understanding of how we get these particular definitions of commonalities across physics. And with that, I am done.
Thank you, Terry.
Thank you, Helen.
Um, I notice George has a question. Are the forward and backward motions a way to balance the books and maintain the conservation laws, charge, mass?
Okay, could you repeat I didn't quite get the last part of that.
Are the forward and backward motions a way to balance the books and maintain the conservation laws, charge, mass, and etc.?
Yeah, yes, this is, and that's what Wheeler and Feynman, I think, really, I think they surprised themselves with that series of papers, because when they first went into it, said they were both going like, this can't work. We're, we're we're playing games with causality, and they knew it. They knew it when they were going into it. And yet, the more they went into it, and the 1949 paper kind of being the end of Wheeler's definitions of that, he kind of said like, yeah, there's something really interesting going on, that is this reconciliation thing. And of course, Fine and Wheeler kind of ended at that point in that, at least the papers that I've seen, the collaboration with Feynman. But Feynman went on, and if you want to look at the variational methods, they are a much less scary way of saying the same thing. But variational methods still say that I have a point here and I have a point there, and they're way the heck far apart in time, maybe like a billion years apart in time, and they're one unit. So even though the variational methods kind of hide this dependence on the future, not really. It's still there. And Feynman did it and took it to the point where he could predict particle properties with exquisite precision. So again, this is not just a casual concept. This is something that has experimental backing to it as a method for explaining how things work. Other questions?
I see Ron has a question.
Yeah, Terry, I don't know, this might sound naive, but this concept of a photon moving in a particular direction as a wave, and that wave is traveling at the speed of light, but there's other wave going in the opposite direction.
Mm-hmm.
Is it so? Does that provide a basis for the concept of the wave going forward defines the speed of light as an absolute, and the wave behind it, does that define absolute zero speed?
And the answer in that was how an interplay between backward speed of light, because it is speed of light, it follows Maxwell's equation. So the advanced wave is a speed of light phenomenon, but in the wrong direction. And I'll be honest, I can't wrap my mind around exactly what the full set of implications of that are, but I think it's something that should be explored uh, in in some new ways, with more of an emphasis on the effect, for instance, on quantization. I put that hypothesis that this is the basis for quantization, and I think we need to look at that more carefully. Uh, One reason why yeah, so I think that's an intriguing area, and I think it has to do with why the overall space is unstable. I think this is a precarious situation on these particles, these waves in both directions, because one way or the other, if they're pushed, they have to come to some conclusion. I mentioned another idea from that I've talked about many times in other things, but people talk about observation as being a a cryptic thing that requires a universe. Wheeler was one of them, a universal observer and stuff like that. And if some of you have followed some of what I say is, I am as opposite of that as you can imagine. I would make the assertion instead that observation is nothing more than momentum exchange, nothing more. It's not some mysterious force. When two particles exchange momentum, they know where the other particle is. That's observation. It just is. When you put a hydrogen atom next to a proton, they have a force attraction that constantly accelerates them around each other. And acceleration is bumping, is momentum change. And remember in the book, in my book, that's observation. So think about this. If you put an atom in the middle of deep space, does it quantum delocalize? Yes, it does. You don't know where it is. I mean, if you leave it out there long enough, it could be in a volume a light year wide, and it's in a quantum state. It can reflect as a wave in that quantum state over an enormous area. It could be diffracted through a gravitational lens over that enormous area. Meanwhile, how are the electron and the proton doing? Are they delocalizing away from each other? No, they're not. Why do they not delocalize away from each other? Because they're constantly observing each other through momentum. It is not a complicated concept. It says that if you exchange momentum, every time you exchange momentum, you say, I bumped you, you bumped me, I know where you are, you know where I am. There's no high level entity, there's no magic in this. It's just momentum exchange. The reason we don't notice it is because classical physics is built out of this. This is what classical physics is. So the irony is that this is essentially asserting that classical physics is the most quantum of all physics because it is the physics of systems that are constantly observing each other at incredible detail, which I think Boltzmann would have liked that idea because Boltzmann, of course, thought thermodynamics was the essence of time. Well, yeah, because if thermodynamics, its observation is constantly going on at an incredibly detailed level, to give the properties we think of just ordinary physics, then sure, there's a powerful connection with that. Other
Uh,
question?
Thanks. I'm just thinking of it in terms of like if something is moving away from you, but it's emitting something back at you, it's
Yes.
almost like it's building a standing wave that isn't moving anymore.
And, and
And
I like where you're going with that.
yeah,
And essentially I'm saying like, yeah, this has got to be part of this whole
and if that's
formation.
true, it begs the question, is the universe full of these standing waves that are just zero speed? And
Well, yeah,
do they just decay over time? And or
I
where do they go?
in that I would agree with it because that is what a photon is. A photon is by its own definition has zero time. And this is something you see in Feynman. If you read through Feynman, he always is adamant about that point. A photon interaction between this point and this point to the photon takes zero time. And you'll see this in QED, you'll see it in his lectures. And he doesn't debate it or anything. You accept that as a given. So the standing wave you're talking about, I would say, is the photon. It's the variational version of the photon. So you're creating a standing wave field. So I think you're onto something with that. That becomes what we think of as the timeless photon interaction between part A and part B, where they suddenly, without an elapse of time, as far as photons concerned, exchange momentum, bump each other, quantum collapse each other. So, we become real, but also the future becomes real. Some part of it, some tiny little piece of it, not the whole thing. it's not everything's not wrapped up. This is a lot more complicated than that, but it's still interesting. It's not a neither predestination nor free will, but it's got some just beautiful options.
Once again, very thought-provoking. Thank you, Terry.
Well, thank you for the question. I like the way you phrased that. I hadn't thought of it that way, but yeah, there's we have a defined phenomenon which is known as a zero time and essentially standing wave from the variational from the Lagrangian viewpoint. It's a standing wave. Yeah. So cool.
Thanks again.
I noticed a question from Carl. Wouldn't this break rules of special relativity by having information travel faster than speed of light. For example, the photon hitting the planet many years in the future, but is still negotiated at this present.
Right. What happens is that there's this concept called information, and the information is the part that cannot travel, at least information as we know it, cannot travel faster than the speed of light. So obviously, if you have forward waves coming backwards, advanced waves coming backwards in time, you're playing games with the idea of light speed limitations. Something in the future is affecting you like right now, which I would argue is actually the truth for all of us, that we're being affected by issues in the future that we don't know about. But what you can't do, at least by any mechanism that we can see, and certainly by the physics itself, is a transfer of information, because the information is the classical physics and information are like tied like very tightly together. You can't separate the two. The ability to create information is the ability to create time, is the ability to create causality. You can't separate those concepts. So if you're talking about sending a signal backwards in time, a signal that's detectable and measurable as an implication, that gets trickier. Although, again, this would be delightful for people to explore in more detail and saying, like, well, what does it mean? But again, that recoil effect is not fully captured in some of the equations. There's a little fuzziness about saying, well, how exactly does that work? Inside of that fuzziness, there's probably some issues of how this interaction with the future works. But for conventional causal information, that's the part that triggers these collapses. So when you do the Wheeler paradox, where you try to get the little lever to swivel in the way and block the ball, that is creating a situation where it would be a paradox, and it's preventing that. So the necessity of creating information essentially locks you out of creating these parallel definitions of what time is. The universe seems very conservative about the definition of time. It says, I only want one time. I'll tolerate little variations on it for a while, but in the end, it's once you create the information, it's locked. And it's, and that's right. That's my bottom line. I won't let you get out of that. So I think there's fascinating issues, and again, I would promote these kinds of explorations as a way of exploring. So, is there a way to transfer something that we would consider useful that's not what we would qualify as Kolmogorov complexity or the usual definitions of information? And that's a trickier question. There could be things involved with this. Quantum computing, the fact that we can do some levels of quantum computing argues right there that biological that there's some way of bending these probabilities. I love biological systems, so they're always bending probabilities. We call them enzymes, and we treat them as if they're mundane, but the actual mechanical representation of systems like that is, we would have a hard time building a physical machine that does what an enzyme does. The enzymes just seem to kind of, just they're able to do things with a probability that we would find impossible to work with. So I think there's clues also in biochemistry that certain configurations can make some kind of better use of something. Call it quantum computation, but there's some kind of relationship there. Other questions?
I noticed Dr. Duda, he keep posting some links, and one of the question, but a lot of questions come and say photon is wave carrying energy, momentum, and angular momentum, like wave behind marine propeller. Yeah.
So I will talk about this tomorrow, but generally, thank you for very nice talk. So yeah, generally, while for electromagnetics it is more difficult. I think for gravitational waves it's much easier to maybe also observe advanced waves. So I have asked you. So because the problem is that for electromagnetics there is a difference between transmitter and receiver. In time symmetry they are switched. So we should be careful about here. But LIGO just measures length, and length is asymmetric. So it should see both retarded and advanced waves if they exist. My point is that maybe already some of events seen by LIGO might be advanced. So it has seen only like 400 events, and only one had a electromagnetic counterpart. The remaining 13, nearly 400 could be advanced because we haven't seen electromagnetic counterparts. So there are many arguments that some of events of LIGO might be already advanced. So one is the lack of electromagnetic counterpart, and this is the clearest. Another argument is that there are some events which seem too early to be retarded. Like there are some mergers which need much more time, so maybe they're not retarded, but maybe they're advanced. And there is also the third time of argument that there is this there are these timing arrays. They see these vibrations of the universe, and they say they are caused by supermassive black holes. However, the number is insufficient now. So again, so should we consider only the past supermassive black holes, or maybe also the future from advanced waves? So there are many
I would agree.
arguments. There are many arguments that LIGO might already see advanced waves. And this is really difficult question. If given event is retarded or advanced, they automatically assume without any reflections that they are retarded. But if you ask, they could be advanced, and it's very difficult to distinguish them.
I look forward to your talk tomorrow. And by the way, I would
Thanks.
encourage people to go to Jarek's talk tomorrow. If you want to dive in deeper in some of the mathematical issues on this, extraordinary mathematician and with good track record for a lot of stuff. So I look forward to your talk tomorrow. And I just think this is we need to explore the nature of time a lot more deeply and the wave structure of time. We're going to put it that way. So I think we're missing some possibilities there. So look forward to your talk.
Okay.
Eric, can I ask a question?
Sure.
I got slightly a bit mechanistic view
I
of
can't
the
quite
universe.
hear. Could you increase the? I can't quite hear you. Sorry.
I say I have a kind of a mechanistic view of the universe. I sometimes think that universe might be a kind of metamaterial universe, where what we perceive as past, present, and future might be already physically connected. So what you see as waves going forward and backward, it may be just a kind of waves, elastic waves, which are reflecting back and forward, back and forward. So
Yeah.
the same what we perceive as time as well as time reversal. It is just waves, elastic waves. The speed of light itself is an elastic wave of the stuff of the universe itself, not a constant in isolation. Is a property of the universe, physical entity.
Yeah. One of the things when and again, this is somewhat accidental. Originally, this talk was going to be focused more on sparse information and bottom up inertial frame emergence, because there's yeah, I'm going to avoid it. That's a fun area. That's a fun area, especially the idea of microscopic domains of space-time emerging. And by the way, I think it's connected with this because when you look at things like quantum field theory, there's a concept of space. There's a concept of creation of space of particles. I think we're seeing into this more amorphous wave structure that you're talking about. In other words, when you have a well-defined inertial frame, I'm betting that inertial frame has a very well-developed structure of forward, of advanced and forward and advanced. I tend to use the word forward instead of retarded, just because I don't know. It comes from camshaft terminology, but forward and advanced waves. But I think if you look at that, I think there's it's hard not to think there's some kind of connection there, that a well-defined inertial frame, and the inertial frames can occur at multiple levels. Don't let anybody tell you that there's only one inertial frame, because everybody's moving. You have multiple inertial frames apply to every event. And they're not just isolated and you just ignore the other ones. It doesn't work that way. Everything's embedded in causality. If you have a train moving at nearly the speed of light, it's still observable. Every clock on it, you can set it up so you can measure exactly what it is at a moment in your time. So that says that whatever their measurement is still embedded in your frame. So you have these multiple directions, the multiple levels of frames, but within each of those frames, I think there's a connection that ties in with things like quantum field theory, where everybody's in agreement. The wave structures are kind of resonating with each other and giving a good definition. So I think there's some interesting stuff going on with that. But yeah, no disagreement about the idea that there's something more complicated going on, and it involves things that are not at all what we think of as the usual speed of light. And yet, that speed of light is so powerful as a tool for understanding what is going on. So that too is a connection. Information ties us to this concept of a speed of light very, very powerfully.
Thank you. Thank you.
Other questions?
Yeah, I noticed George, he posed a question like Shannon information is about a single transmitter and single receive. Kolmogorov training complexity is about a whole system. The relationship between this is not clear to me.
Like Kolmogorov complexity, because for me, for instance, for me, when people have questions now about large language models, I reflexively go to Kolmogorov complexity, because Kolmogorov complexity says, what is the single most reduced form of the information in the total system? And it's a very hard question, because if you saw a string out of the middle of the billionth digits of pi, the question was about Kolmogorov complexity versus Shannon. Shannon is transmission. Kolmogorov is essentially a measure of the entire complexity of the system in its most reduced form. And the comment I was making earlier is that one of my cautions about large language model systems, AI based on large language models, is the Kolmogorov complexity of those systems is always pretty much exactly the same as the training data that went into it. So you can recover whatever you trained it on, but that's it. Anything beyond that tends to be a random combination, a very convincing random combination, but you don't have any further insights beyond what was actually in the training data, which is why they talk about scaling them so much. You want to scale them up to huge size so you have more answers, but you still just wind up reaching the threshold. You still have a finite Kolmogorov complexity of an LM system by its nature. That's what it is. It's a carefully factored storage of a huge amount of data, and you can still recover the original data. You can still recover entire books because that's what's in it. So occasionally I'll refer to an LLM as a database, and people take offense at me because I do that. And I was going like, why do I refer to it? And I realized it was because of Kolmogorov complexity. In physics, I think both of those concepts are important and relevant. The Shannon, of course, is more the transmission side. And is there a forward backward Shannon definition? Probably there is. There's some kind of thing where you have advanced and forward waves that are interacting in some fashion, occasionally forming discrete units like photons. A photon is a collapse, as we talked about earlier. But I think there's an intriguing options for doing that. Kolmogorov complexity, that's got to be a part of some of this. The definitions of an inertial frame is going to have a Kolmogorov complexity. So I love Kolmogorov. He just is an amazing writer. If you've never heard of him or you're not familiar with him and you're interested in information, look at Kolmogorov's work. It is a very different take from sham. Other questions?
George should say thank you.
Thank you.
Another excellent, thought-provoking presentation. Much thanks, Terry.
Well, thank you, Ron. Appreciate it. Always good to see your, I love your logo. There's something about that logo I really like. It's just, it's colorful in just the right way.
You make my
So-
day, Terry. Thank you.
Any other questions? Going once? Okay, why don't we give it a wrap there? And thank you everybody for participating. It's great questions. Really enjoyed it. And looking
Yes.
forward to Jared talk tomorrow.
Tomorrow, yes, tomorrow at 10.
Yes, it's tomorrow. Everybody remember tomorrow.
Thanks, George.
Yes. And Jordan said, thank you, Terry. Great talk.
Thank you all.
Thank you. And see you tomorrow.
See you guys tomorrow.